All right, welcome to day 10 of Unit 1. We've got the homework assignment posted on top there. Today we're going to talk about differentials and error in estimation. So from the team problems, the last two are listed there, your answers, and I'll uh, pause on the worked out solutions for a second as well. If you have questions, get in touch. You can post questions on the content section of the discussion board on Schoology. So there's the worked out solution for 3. There's part of the worked out solution for 4. And there's the rest of it. So you can pause those and go through your work if you've made an error somewhere and want to find where your error is. All right, so today's topic starts out with differentials. So our notation for a derivative dy over dx. So you can think of that as a ratio. So as something over something. When you write the dy or the dx individually, those are referred to as differentials. The dy is representing some really small change in y and some really small change in x. And dy over dx you can think of as when we make a small change in x, what is the resulting approximate small change in y? So we've seen in previous units that dy over dx is the same as f prime of x. Well, knowing that we can write dy over dx as a ratio, then we could multiply that dx over, and that gets the dy by itself. So dy would be our differential. It's representing the little bit of change in the y value, that approximate change. And you can represent it with the derivative of your function times dx. So first thing we're going to do is we're going to practice actually calculating that differential. Then we'll look and see the meaning of it a little bit more, and then we'll apply it in some practical ways. So to start out, we want to find our differential. In other words, we want to get that dy alone. So we'll take our derivative to start out. Dy over dx would equal 3x squared. And then just multiply the dx over to get the dy alone. So we'll talk about on the next slide, but again, dy is the approximate change in the y value when there's a little bit of change in the x value. And let's look on the right side of that equation there and see what things are determining that little bit of change in y. Well, the two things that are determining it are how much change in the x there is, so that's our dx, and also the derivative of the function. Well, think back to what a derivative of a function is. The derivative of a function is a slope of a tangent line. And in most cases, the slope of your tangent line is dependent on what x value you're at on the function. So our little bit of change in y is dependent on how much we changed in the x, but also what the slope of the tangent line is at that specific x value. Going to the second one, we'll take our derivative. We've got to do some chain rule here. Derivative of sine is cos. Keep the inside the same, times the derivative of the inside. So multiply the dx over. And I'm just going to neaten things up a bit by putting the 2 out front. And that would be our differential. In our third example, we got to do quotient rule. So we've got to do quotient rule for our derivative. So there's our quotient rule. We want to get the dy alone, but before we do that, let's neaten up the quotient rule a little bit. If we distribute the 2x, we'll have 2x squared plus 2x minus x squared. And then this will just be x squared plus 2x over x plus 1 squared. And to finish off, to get our differential, we'll just multiply the dx over. Again, that differential we'll see on the next slide represents the approximate little bit of change in the y value that occurs when you change the x value by a little bit. And the slope of the tangent line at that original x value plays a role. So here's a visual to show you what we are working with the differential. Remember, the differential is our dy. The dy is determined by the change in the y value of the tangent line. Delta y represents the actual change in the function. Differential calculus focuses on equations and slopes of tangent lines. You've hopefully seen before that tangent line equations are good approximations of our curve near the point of tangency. That's the idea of local linearization. If you zoom in close enough at the point of tangency, the tangent line and the curve will look really similar. So, as long as that dx or delta x, they both represent the same thing in this case, as long as that dx or delta x is not that big, the slope of the tangent line should be a pretty good approximation of the change of the actual function. And because lines are a lot easier to work with than other curves, that is why we would want to do this. We could use differentials to approximate really nasty values. And by using the differentials, the process isn't going to be too bad. So an application of that. So we're going to use differentials to approximate the difference between square root of 9 and square root of 10. You're almost always going to have one nice value that's your point of tangency. So square root of 9 is a nice value. So essentially, we know that that point is 9 comma 3. And that 3 is coming from doing square root of 9. Well, we want to approximate that value there. We know it is 10 comma 10 comma something, and it's whatever square root of 10 is. So we want to know, we know it's a little bit more than 3, but we want to get a better approximation of that. Well, the actual amount that it changes from square root of 9 to square root of 10 is that black amount. We will be able to approximate that purple amount by using differentials. It's a little bit extra in this case because it's concave down. Okay, if it was concave up, it would be a little bit of an underestimate. But we'll be able to use our tangent line to approximate how much that changes, and that change is the dy. So just like we did before, we're going to do our differential to start out. So multiplying the dx over and neatening up, this will be 1 over 2 radical x times dx. So dy is the approximate change in the y value. So we need to find a numerical value of dy now. Well, to do that, in for x, you put whatever the x value was at the point of tangency, or in other words, the nice x value. And for us, that was the 9. And the reason we want to do that is the x value that's determining the slope of the tangent line. The slope of the tangent line is determined by the x value at the point of tangency, because the slope of the tangent line and the slope of the curve will be identical there. And then dx is represented by the change in the x. Well, if we go from square root of 9 to square root of 10, the x value went from 9 to 10. So that's an increase in 1. So we would just have 1 for that. Now, it's not always going to be 1. If we wanted, say, square root of 9.5, that would have been 0.5. If we wanted square root of 8.5, that would have been negative 0.5, because it would have been 0.5 below our nice x value. So therefore, our dy just becomes 1/6. So 1/6 is a nice rational number. A square root of 10 is an irrational number. So the differentials gives us something that's pretty nice to look at and wrap our heads around. Okay, if we go from square root of 9 to square root of 10, the y value should increase by approximately 1/6. And if you wanted to do square root of 10 minus square root of 9, or in other words, square root of 10 minus 3, and compare that decimal to the decimal value of 1/6, you can see that it is pretty similar. All right, so here's another example. We've got a curve here. So some things we can determine from the curve. 3, 3 is the point of tangency. So we know that f of 3 is just 3. F prime of 3 represents the slope of the tangent line at our point of tangency. Well, we can figure that out by looking at the second point they give us on the tangent line and just doing the slope. From 1 to 3, you went up 2 and over 3, so your slope of that is just 2/3. So we're going to use that to approximate f of 2.9. Now notice we don't have the equation of that curve, but we know from what we've seen before that the differential, the amount it's changing, is represented by f prime of x times dx. Well, our x that we're using is 3. And then dx is how far we are from 3. So in this case, dy, we know f prime of 3 was just 2/3. And if we're dealing with f of 2.9, that means we want to go down 0.1, or in other words, 1/10. So we're going to multiply this by negative 1/10. So this means that our dy is negative 2/30, or in other words, negative 1/15. Now keep in mind, this is the approximate change in the y value. Last question, that's what they wanted. This question, that's not what they want. They want to actually know what is the new y value. Well, to figure that out now, we just take our y value at the point of tangency and apply the approximate change in the y value to that. So you could either call this 2 and 14/15, or you could call it 44/15. So again, those are nice rational numbers. Pretty easy to work with. Next example, f of 3.2. Our slope of our tangent line at the point of tangency is still 2/3. This time we increased by 0.2, which is the same as positive 1/5. So dy would equal 2/15 in this case. That's the approximate change in our y value. Apply that to the nice y value. So 3 plus 2/15 will either give us 3 and 2/15 or 47/15. Now notice that part of the graph is concave down. So no matter if we're moving a little bit to the left of x equals 3 or a little bit to the right of x equals 3, both those values are going to be over estimates. That's just something to always think about when you're using something to make an estimate. Is this an overestimate or is it an underestimate? And a lot of times there's features of the graph or the function you're working with that can tell you that. All right, the last topic we'll look at today is using the differentials to estimate the propagated error. Now, what propagated error means is the difference between the exact value and the measured value. So if you've got some object, you take out a tape measure and you measure it, there's a chance that your measurement could be off by a little bit. So that's what we're approximating here. Now, by you measuring, say, a length a little bit off, if you then use that incorrect length to calculate something else, like an area or a volume, well, basically that error is going to be compounded in the calculation and change that new value you're calculating as well. So the propagated error basically shows us how the little error in measurement could be carried through. What's the effect that that could have? So we've got a side of a square, and we're saying that they're measured to be 4 inches. And it's correct within a 1/4 inch. So it may be a 1/4 inch below that, could be a 1/4 inch above that. And we want to see what the possible error is in the area. Well, the error is essentially the approximate change in the area. The approximate change is just a differential. So we're going to start with our area equation for a square, a equals x squared, and we're going to do our differential. So dA over dx equals 2x. So therefore, our differential for the area is 2x times dx. So what this is telling us is the approximate change in the area is determined by 2 times whatever the measured amount is, times the amount that could be off by. So for us, that's 2 times 4, because 4 was the measured amount, times what that could be off by. So we had plus or minus a fourth. So therefore, the potential change in the area is plus or minus 2 inches. Now, when we're finding the error, it's the maximum possible error. So yeah, this measurement is correct to a 1/4 inch. Well, maybe the error was 1/8 of an inch. So when we're identifying this, our final answer, it's what that maximum possible error could have been. And that idea will come into play in the next question, because if you have multiple terms that are adding or subtracting with those pluses or minuses, we're just looking what's the combo of signs that will show the maximum possible error that we have. So that's a basic example of that. We'll look at one more example in this video. So we've got a cylinder. We're measuring the radius to be 2 meters, the height to be 5 meters, and both of them are, we know they're correct within 1/10 of a meter. So it could be in either direction. We want to estimate the volume of the cylinder. Well, hopefully you recall that volume of a cylinder is just a circle times the height. So we're going to start out, we're going to find the differential. We're going to find our dV. So there are a couple ways we can do that, because a question you might be asking yourself is, what variable should we take the derivative with respect to? In the ones we've seen before, on the right side, there was always one variable. So that was our d whatever in the denominator. But here on the right, we have multiple variables. And I'm going to show you 3 different ways you can do it. And you can do it any of those ways, or you can kind of do a shortcut to what it's going to end up as. So let's look at case 1. Let's say we did it for r. So we're going to do dv over dr. So that means r is like an x normally is. So if you take a derivative of an r in this case, don't have to do anything special, but any other variables, you're doing implicit differentiation. So we got to do product rule. So pi r squared's derivative is 2 pi r times the regular h plus pi r squared. Now the derivative of h is 1, but that's not the derivative we're taking with respect to, so you got to multiply by dh over dr. Kind of like when you do implicit differentiation with x's and y's. If you take a derivative of a y when you're doing it with respect to x, you need to multiply afterwards by dy over dx. So similar idea here. So then what we would do is we would multiply everything by dr. So we would get dv equals 2 pi rh times dr plus, in the second term when we multiply by dr, it divides out with the dr in the denominator, so we just get pi r squared dh. So that is case 1. And we'll come back to it. That's the differential we're going to use to actually find the error, but I just want to show you the 3 ways you could think about it. So case 2, what if we had let h be the variable we are taking the derivative with respect to? Well, in that case, we would have dv over dh. We would have 2 pi r, but that's not the r is not the variable we're taking the derivative with respect to, so you'd have to multiply by dr over dh times your regular h plus regular pi r squared times the derivative of h, which is just 1. Don't have to multiply by anything because that's what we're taking the derivative with respect to. So now this time we'll multiply both sides by dh, which will give us dv equals, in that first term, the dh that we're multiplying by and the 1 in the denominator divides out. I'm going to write the h and then the dr, just to make it more clear that it is the same. And then here we get plus pi r squared dh. So notice it's exactly identical to what we got for the differential in case 1. So it doesn't matter which variable you do it with respect to, you're going to get the same answer anyway. Now let me show you case 3. Case 3 is you could pick what is often referred to as a dummy variable. So let's pick just a variable that's not even in the problem. Let's do x. So we could do dv over dx. So that means when we do the derivative of the right side, everything is going to be implicit. So we're going to have 2 pi r times dr over dx times regular h plus regular pi r squared times the derivative of h, which is 1, times dh over dx. Well, now we would just multiply both sides by the dx, giving us dv equals, the dx's divide out, so you have 2 pi r, I'm going to write the h first and then the dr, again just to make it match up. And notice that's identical to all the other ones that we had. So you can think of it any of those ways because you get to the same thing, or notice what happens in the end. Basically, when you do a product rule, whichever part you're taking the derivative of, so whichever variable, so like we had an r, notice that ended up with a dr. When we took a derivative of an h, that ended up with a dh. So if you recognize that, you could also shortcut it and jump right to that. Okay? So it's your choice how you would like to do that. So let's take this and we'll fill in. So dv is equal to 2 pi. R is the measured radius, which they told us was 2 meters. H is the measured height, which they told us was 5 meters. And then the dr is plus or minus 0.1. So for the second part, so I'm out of room there, so I'm just going to carry it down here. So plus, we'll have pi times that radius again, the measured radius squared, times our dh, which was also plus or minus 0.1. So this is what I was talking about with we're looking for the maximum. So basically the maximum error, the maximum dV is going to come from both of them being plus 0.1s or both of them being minus 0.1s. So you can essentially just do the calculation without the plus minus and then bring it back in the end because that would be the maximum of those combos. We want to know what's that greatest possible error. So 2 times 2 is 4, times 5 is 20, times 0.1 is 2, so we'd have 2 pi. 2 squared is 4, times 0.1 is 0.4, so we'd have 0.4 pi. So we end up with dV is plus or minus 2.4 pi, and we've got meters cubed for our units. So again, I showed you the case 1, case 2, case 3. Either you need to pick one of those or just recognize the pattern and you could jump right to your differential. So whichever variable you were taking the derivative of in the product rule, just you end up with d that afterwards. And that's it for differentials.